Alright, so in this problem, we're going to be looking at Molly and her motion relative to a police officer. And so the first thing you really want to do is just draw, a box. Put an M in it. And this represents Molly. And so the first thing we want to do is just provide some sort of direction. And put all the information we know down. Right? Molly is speeding along a straight road. We can draw a straight road. We can draw her having a velocity, a speed vector. And it says speed is 15 meters per second. That's the first piece of information we have. Molly is traveling at 15 meters per second, and we're going to say the positive x direction is to the right. Negative x is to the left. And it says she passes a parked motorcycle police officer. Put a C for cop. And he's parked. So that means his V initial is 0 meters per second. And then it says the officer accelerates at 2 meters per second squared. So that way he can accelerate and catch up to Molly. And we know, just from a general, conceptual point of view, that if he's going to catch Molly, he's going to have to go faster than 15 meters per second if he's ever going to have a chance of catching up to her. He has to go a little faster than she is. So we know his top speed that we're going to be finding later. We know that it should be greater than 15 meters per second. So just by, conceptually thinking about these problems, you can usually get a feel for, is this a reasonable answer? And so first off, we don't have an acceleration for Molly, so we can say her acceleration is 0 meters per second. And so now we have the initial position, right? And this is at t0, at t equals 0. Molly and the cop are at the same position. X Molly equals X cop. The position of Molly is the same as the position of the cop. And at, we can draw another picture, sort of down the road. And the cop car has now caught up to Molly. And so at T final, let's put an F, and we'll go back and put an I on T initial. So T final equals, well, we don't know it's 0. So we don't really know what the final time is. But we know that there is a time when the cop will catch Molly. That's part of part A, is determine the time it takes to reach Molly. And so we're going to see how long, what is TF when the cop and Molly have the same position. That is the key, idea that's going to help you solve this problem, is that at time final, that's at the time that is the answer for part A, Molly and the cop have the same position once again. So now that we know they have the same position, well, how do we express x sub m and x sub c, the position of Molly and the position of the cop? Well, we can use the equation x equals, so the position final, you could say, is initial position, x sub 0, plus initial velocity times the time, plus 1/2 times acceleration times time squared. And so this equation lets us decipher what Molly's final position and the cop's final position are. And we can sort of create the relationship where Molly's position is equal to the cop's position. And so this is just the general equation. And now let's go ahead and see what is Molly's position. Well, Molly's initial position, x sub 0, well, we're going to say the origin, since we can pick where the origin is, we're going to say that's where Molly and the cop start. That means they both have initial positions of 0. Now Molly has initial velocity of 15 meters per second. And that's multiplied by time. Now we add 1/2 times her acceleration, and Molly has an acceleration of 0 times t squared. And so this simplifies down to just 15t. Now we go on to the position of the cop car. And we see that just like Molly, the position is 0, the initial position. And now we have to add initial velocity, which cop has a 0 initial velocity times time, plus 1/2 at squared. So the acceleration for the cop is actually 2 meters per second squared times time squared. And so this ends up just being time squared. And so now we remember we had the position of Molly equals the position of the cop. So we can actually just say xm equals 15t, xc equals t squared, we can set them equal to each other. 15t equals t squared. And by factoring out a t from both sides, we get t equals 15. Now, we didn't put units in our equation. And we did this because putting units in the equations can make them very complicated. And just doing the numerical analysis and understanding that time will always have units of seconds can make these problems a lot simpler. Right? Not having to worry about calculation of units and numbers both in the same process. I mean, this makes it a lot easier. You just tag on that seconds that we're expecting. And that answers part A. We now know it takes 15 seconds for the police officer to catch up to Molly's position. Now, we're on to part B. So, what is the speed and total displacement of the officer as he overtakes Molly? So what we're looking at here is what is the total distance that he travels, right? He travels from here all the way back to the origin 0, 0. And this is distance D. So how do we find the distance he traveled? Well, we can look at the final position of the cop, right? If his position is given by the function t squared, he's traveling for 15 seconds, we can go ahead and say that, let's get some more space. We can go ahead and say that x sub cop, the final position of the cop is just 15 squared, which is 225 meters. So that means he travels 225 meters. And we know that both Molly and the cop have that same displacement. But this isn't the entire answer. We also have to find the speed. So what is the speed of the cop car? Well, we have the equation v final plus v initial plus at. Now we know we're trying to find v final, that's our unknown. The initial velocity of the cop car is 0. The cop car accelerates at 2 meters per second squared, and it travels for 15 seconds. And so, this is a calculator, do it in your head, and then up to the final velocity of 30 meters per second. And so, here we have found how long it took the cop to catch up to Molly, to catch her, how far they traveled, as well as the top speed the cop reaches. And you can see he's going to reach 30 meters per second. That's a lot faster than Molly is traveling, and that's because he has to go a lot faster to catch back up. But she's putting distance between them right off the bat while he's just not moving. Alright.